2 calcs in 1, so it'll be a doozy. Drunk on power and with no real control of the Gura Gura, Teach sends a tsunami at Sabaudi Archipelago. Chapter number 579. First, we need to determine the distance between Marineford and Sabaudi. This graph shows the structure of the trifecta that is Marineford, Impel Down, and Enies Lobby. Important to note though that none of the islands are visible to one another. They are all beyond the horizon to each other. Once again, in my video I determined the distance to the horizon is over 10 million meters in length, so I'll use that as how far apart these 3 islands are to each other, as a lowball at least. Getting the distances in pixels, I get an average of 56.33 pixels per horizon distance. This would mean the per pixel value is around 188.32 kilometers a pixel. While the Viz translation omits this, the fan translation says that the tsunami is coming towards the southern coast of the island. I made sure to check if the Japanese RA mentions it too, and yes, it actually does. Nanbo Engen means southern coast. Now, let's think about the structure of the One Piece world. The Grand Line is a horizontal line wrapping around the planet, with the calm belt wrapped around that. On the graph, we see that the calm belt is to the right of Marineford. This means that the right of Marineford is either north or south. But we know 2 things. 1. Sabaudi is an island on the Grand Line, and 2. The tsunami coming from Marineford is hitting Sabaudi's south side. So, the right of Marineford must be south, which means that the tsunami is moving towards the left of Marineford. We don't know how far Sabaudi Archipelago is relative to Marineford, but using the graph, it must be at least 30,507 kilometers away. Now that we have a distance, we can move on to the actual calculations. But before I do that, a huge thanks to Business Email for helping me with this calc. I could have never done it without his help. Another huge help was from the 2013 Whitebeard Quakes calc from God Movement. Without this prototype to work off of, it would have taken so much longer to finish this. The research for this was already strenuous, but without a framework to work off of, it would have been nightmarish. And now let's talk quakes. According to this site, the following formula is used to gain the Richter magnitude of an earthquake. A is the amplitude in millimeters and delta, the triangle, T is time difference in seconds. Now, I know this formula may look scary, especially for someone like me who hasn't done logarithmics since high school, but bear with me. Here are some of the basic stuff you gotta know. First, the terms epicenter and hypocenter. The epicenter being the center of an earthquake above ground, and the hypocenter being where the earthquake originates underground. This thing right here is what we call a seismometer. It allows us to record the amplitude of earthquakes by turning vibrations into electrical signals that draw a seismograph. The seismograph has 2 particular waves, the primary and secondary waves. They're also called P and S waves. P waves are faster, but S waves are what actually affect the surface. The time between the 2 waves' arrivals is our time difference, our delta T. This right here is what we call a nomogram. It's a graph used to measure characteristics of an earthquake given certain other characteristics. For example, a seismic station located 60 kilometers from the epicenter of an earthquake recorded the maximum height of the S waves to be 50 millimeters. What was the Richter magnitude of this earthquake? To solve this, we simply draw a line from 60 kilometers all the way to 50 millimeters, and that gives us a magnitude of 4.5. Simple, right? Well, Whitebeard is a weird case. As GM stated in his own calc, Whitebeard is both the epicenter and the hypocenter. Taking this into account, he said the following in the calc. I drew through 2.5 as that is the most we can deduce. However, with the nomogram going up a single unit in magnitude increases the amplitude by 10 times. Why? It's logarithmic. So, 2.5 equals 50 millimeters, 3.5 equals 500 millimeters, 4.5 equals 5,000 millimeters. Teach would be just as special as Whitebeard in this case since he uses the Gura Gura the same way. So this applies to him just as well. At 2.5 on the Richter magnitude scale, GM determined the amplitude is at 50 millimeters. But how strong were Teach's earthquakes? How high would they be on the Richter scale? Well, as we can see in this scan, the tsunamis Teach created were easily hundreds of meters tall. We know this because we have San Juan Wolf's height thanks to his Viver card being 180 meters. Despite that height, he was still able to hide behind the Marineford base, and it wasn't until he moved around it that he was seen. The largest tsunamis we see are behind the Marineford building, and even then they seem to be around the height of the approximately 200-meter high building, but because they are farther from the point of view than Marineford, they would look a lot smaller than they actually are. As such, they are definitely higher than 200 meters. To take a real-life example, the 2001 Tohoku earthquake was a magnitude 9 to 9.1 earthquake, and the tsunamis it caused were up to 40.5 meters in height. Given that fact, I'll use 9.5 on the Richter scale for Teach's quakes as a safe lowball. As GM noted, the Richter scale is a logarithm. As such, these are our values for the Richter scale. And given we're using 9.5 on the Richter scale, this gives us an amplitude of 500 million millimeters. And now that we have the amplitude, we just need delta t to do the formula. As I said earlier, delta t is the time difference between S and P waves on the seismograph. Alas, we have no such thing, so what can we do? Does that mean the calc is a bust? Well, when there's a will, there's a way. In comes this lecture about seismology that gives a very helpful formula. You can find how far an earthquake moved in miles if you just have delta t. All you have to do is multiply it by 5.7. Using basic algebra, I can find delta t by the following formula. S minus p, or delta t, equals the distance the earthquake traveled in miles divided by 5.7. Doing just that gives us a time difference of 3,325.65 seconds. This is our delta t. Now we finally go back to our formula. In the end, we get a final result of 19.15 for our magnitude. Putting that in the earthquake power calculator, and we get a result of 0.81 yotatons of TNT. Solidly high planet